I'm not talking about respiratory chains as Nick suggested, because that would mean that I'm putting forward the things that differentiate us, Nick and me. I will more take advantage of what he already said about the energy aspect, and since you're prepared now, rub that in and do what Nick in a way cowardly avoided, that is to make clear to which point this is different from the traditional approach to the origin of life. Okay, so fortunately Nick made it very easy for me because he already had a couple of slides that I would have shown you too, so I can speak more slowly maybe. I'm a biologist since 25 years, as Nick said, is himself. But I'm trained as a physicist, so there is maybe a different approach that comes over here. And I was thinking, since this is a completely mixed audience, I would try to just have fun and bring in both my physical aspect and my biology aspect, which is not always easy. So I mean, for the biologist, the word dissipative structure anyway is a reason to leave the room, which is probably not true for the physicist. So let's see, the physicist can go to sleep for the moment, and I will tell you when to wake up again. Okay, so this dichotomy that I want to say, this leaving the traditional way to think of the origin of life is connected to what people in the last couple of decades were thinking of. The way they were addressing the origin of life was they looked at what life was. How was life constructed, made up, and of course it was the organic molecules that came up. Now the organic molecules, then you have all these approaches to find ways to abiotically synthesize these organic molecules. Now, I'm doing microbiology, microbial phylogeny and physiology, and it's mainly the physiologist's point of view which is important there. If you really look at microbiology and you look what life does, you get two different messages. There is an enormous amount of bacteria out there that don't need the organics. They just make them from scratch. They just need CO2, as Nick just said for the methanogens. So just give them CO2 and of course ammonia, all the other elements, but they don't need organic molecules. They don't need lipids, they don't need sugars, all that stuff. They do them. But they clearly all the time need a redox disequilibrium. This is what Nick already mentioned, and that's just a cartoon again of what Nick showed you with the mitochondrial respiratory chain. And I would disagree with Nick that we do not strip electrons of the donor, because that would mean that there is some work to get in to get the electrons out. No, this is a reductant which is more reducing, and that's downhill. That's a thermodynamic process that wants to occur. So there's energy in there. And the whole thing works like a battery. Now, of course, that was true for us. This is true for the rest of the microbes, and there is certainly many other mechanisms. There is donors and acceptors all over the place. There's different types of respiratory chains, and there I'm talking about respiratory chains, but that would be the only time. And it's not eating and breathing is not the same thing in these cases, because some of the donors are gases and some of the acceptors may be solids. So, but what is always the same is you have an electron donor and reductant, and you have an oxidant. Okay, so to summarize it up, when you look at microbiology, what you see is bacteria, prokaryotes, need redox energy. They don't need the organic molecules. Okay, so from the point of view of physics, of course, the energy point is clear. There's nothing happening without the energy, and this is even the biologists will remember the second law of thermodynamics. So the second law of thermodynamics clearly states that in a closed system, everything tends to increasing delta S, the entropy. Now, life, if you put a bacterium into a vessel and you have it grow, what is going to happen is that it generates order from disorder. It just takes all the elements and puts them together to a new cell. So that is clearly somehow at odds with the second law of thermodynamics. And of course it isn't, because it's not a closed system, it's an open system. So you have the delta H that helps you out. There is enthalpy flowing into the system, and that allows the second law to be true. Now, this was already pointed out some 60 years ago by Schrödinger, when he said that life necessarily feeds on negative entropy. So that means on entropy fluxes into the system. Okay, the second law of thermodynamics, so in principle, tells you that life is possible if there is delta H flowing into the system, but it doesn't give you a mechanism. Now that was 120 years ago, and the physicists, many of you in the audience do these kinds of things. They know that complexity in this universe, a rising complexity is not restricted to biology. You have that in many, many different occasions, and so this is just this atmospheric phenomenon. So you can see that there is something structuring, organizing without any biology going on. And that's, there's 60 years of nonlinear thermodynamics that was developed, and culminating with the Nobel Prize to Prigozhin, and in the Nobel Prize attribution there was the word dissipative structures, and here it is. So that's the dreaded word. This is the dissipative structures. Now that's a couple of dissipative structures that physicists know. Peanut cells, known to you maybe if you prepare coffee in the morning. That one is closer to what we are dealing with. You can say that's all atmospheric stuff and fluid things. This is a chemical reaction. This chemical reaction, if you can look at it, it generates order both in space and in time, just from a disequilibrium situation. So that's something that if I showed that to a biologist, he would tell me there is life going on in there. Now the nonlinear thermodynamic people worked out how to under which conditions you can develop complexity in a physical system, and that is, first of all, the energy must be far from equilibrium. So this one won't work if you're here far from the equilibrium state. Then you can get to structure formation, to dissipative structures. You need nonlinear equations, and you also feedback loop help as well. Now that is quite often tedious to work out. This is the chemical reaction for the Belousov-Zhabotinsky reaction, and in there you can define certain elements which actually serve as what is called dissipative engines. So engines, just think of the steam engine that transforms thermal energy into movement, into work. So these engines transform the energy flux into order. Now, the task for the physicists is quite often to define these dissipative engines that specifically on a very small scale do the work. Okay, so, oh, I go the wrong way around. Okay, so now let's return to biology. This is a cell, and if you ask me, you have only two choices. Either you say life violates the second law of thermodynamics, and then you have to come up with different interpretation, different rationalization of that. I'm fine with that. But for me, I think the more reasonable way, or the way I would look at it, is that life, in fact, is a dissipative structure. So, for the biologist, this is something that is just there, a cell. If I look at it like that, what life really is all the electrons flowing through the cell. It's in permanent disequilibrium. And if you're a microbiologist, you will know that once you don't put any nutrients into your vessel, then the cells won't grow. So now we have two different tasks. The first one is to find an environmental setting for the origin of life where you have strong redox gradients, because the redox gradients is what we see in extant life. So the first choice is to say that life also originated from redox gradient. That's the I will go through that quite quickly because we have. So Nick was talking about the hydrothermal vents, and the hydrothermal vents are very interesting because they really look like a cell, and Nick was talking about that, so I can go over that. There's maybe other locales where you can have similar strong disequilibria. I'm fine with that. For the moment, the hydrothermal vents seem to be the most appealing to me. Now, the next step is that just as for the chemical systems or for the atmospheric system, we have to work out the dissipative engines which transform energy into order. So I will, from looking at bioenergetics and what we've seen and other people have seen in extant life, I would try to present a couple of them to you and ask a couple of questions which might be relevant to astrobiology. So what is so great about redox energy? Why doesn't life just originate from thermal gradients, from radioactivity, whatever? So we have to discuss that, and I think there's a lot of discussion that can go on afterwards, but I will propose a couple of ideas to you. The first one is certainly that redox energy is scale independent, whereas if you have temperature and you reduce the scales, then the energy gradient will become smaller and smaller and smaller. This is not the case for redox energy. You can have the donor right next to the acceptor as a molecule. So you can have the same amount of energy at nanoscales next to each other. The other thing is that for life to emerge, you need that these gradients are stable, or at least metastable. And many redox couplers are metastable. So they can stay next to each other for hours or days. There is a couple of reasons for that, high activation barriers, but one of them which I wanted to talk about is cooperative multi-electron redox chemistry, and this becomes important afterwards and for astrobiology maybe. That's the reason why I will go into that a little bit more in detail. So I give you the case of a 2-electron redox compound which goes through 2 different redox states, from the oxidized to the semi-reduced to the fully reduced state. And if you're in an aprotic solvent, then what you would expect is that the first redox transition is easier than the second one, because if you put an electron on, the second electron doesn't want to go on as easily. Now this changes completely when, so that's the first reduction comes before, and if you go the other way around, the first oxidation is at the lower midpoint potential. Now if you put this into an organic solvent, then you have protonations going on, and according to the pK values that are involved in all these species, you can have a very funny phenomenon. This is that because the mass action energy of the proton will change around the redox potential, and you can get to the conditions where actually your second oxidation comes at a lower potential than a first oxidation. Now that's an old stuff for the electrochemists. So I mean, this is the electrochemists can go to sleep now. That is, and that is one of the reasons. I mean, Nadia was mentioning this morning that in aqueous solutions, chemistry is very different and more difficult. That's one of the reasons why the electrochemists avoid aqueous solutions, and they prefer to work in aprotic solvents, because everything is much faster and much easier to understand. So redox cooperativity requires protons. Now redox cooperativity gives you, just to show you that rapidly, imagine you have a 2-electron redox compound and you're in an aprotic solvent. So as we said, the first oxidation is at a lower potential than the second one. So if you have an acceptor there, then this one goes downhill, hexagonic, fine, you get to the semi-reduced state. Now you get a second substance is coming in. This is uphill, and actually it won't go, it will only go to equilibrium, it will go a little bit, but not a lot, so you get equilibration for that. If you're in an aprotic solvent, if you're in a protic solvent in water, then as we said, the first oxidation is at higher potential than the lower one. So this is our first oxidation going on. And this first oxidation won't go. So you never get to the second state. and your equilibration is very slow actually. I mean, you could say there's no equilibration, but if you have the two present at the right time in the right place, two of the same acceptors, then of course it will work. But that makes that this is a very unlikely event, and it will take much more time to happen. So this is why these reactions actually are metastable, and in the lab you can have a 2-electron donor standing next to an acceptor for hours or days, which is eternity for a chemical reaction. Okay, so that's one of the things is metastability. So we don't have to ask what is so special about redox chemistry, redox energy, but the thing is redox chemistry in H2O. That is the interesting thing. So the special thing is, as I said, it's the metastability. The other thing is redox bifurcations that Nick already mentioned. And redox bifurcations is that. So go back to what I showed you already. This is what I showed you. So you need two acceptors at the same time in the same place so that this works. And you can do a funny thing. You can actually have two different 1-electron acceptors. If you have two of them like that, then of course the reaction goes. But you have a very different situation going on in terms of energy. Because from this energy level, you now reduce one which is hexagonic and one which is endergonic. So you decrease the entropy of this system here because you put it to a higher energy level. Okay, so this redox bifurcation, for example, is one of the dissipative engines that you could imagine that were used by life and actually is used by life, because as Nick said, Nick mentioned this in the methanogens, but we have it. You work with redox bifurcation. Mitochondria work with that. And there's many new redox bifurcations that's hyped now. If you're in biology, in bioenergetics, redox bifurcations are in. And to the point where I would say even there is redox bifurcations published which aren't. In extant life, redox bifurcations are mainly done by quinones or flavins. We've shown recently, and other people have done the same thing, that also molybdenum can do these kinds of electrochemical reactions, and tungsten probably also can do. It has not been checked so far. Now this brings me to the next point, which is that if we look at how life works, then we see that metals play an enormous role, and the molybdenum enzymes actually are one of the life. I would claim that they are life's most versatile biocatalysts, and but the molybdenum enzymes are only a part of it. I mean, the vast majority of catalysis is done by metals. So we should, in astrobiology, we should not forget about the metals. And actually, Floris was mentioning this this morning as well, and we come back to that. So what we have to do and we are not yet there, we have to work out how the metals work as dissipative engines. We have an idea for molybdenum, but for most of the others we don't have so far, at least a clear idea. Now, I can basically skip that because that's the proton gradient. Nick was talking about that. A large part in extant life of the redox energy is actually converted into a pH gradient which serves to synthesize ATP. And what you do is you move away the equilibrium, the chemical equilibrium of ATP to by more than a factor of 10 to the 10th. So this is again a way to convert one disequilibrium, which is electrochemical in that case, into a chemical disequilibrium. So that's another engine, and I would argue that it was not ATP, but it was pyrophosphate, but that's only a detail. These things have to be worked out how that might have worked at the origin of life, and that's one of the proposals that we have put forward in the past. But that's not one of the crucial things that I wanted to talk about. I mean, there's other things. So this is the only point where I will disagree with Nick. I would say, well, not even disagree. I would say there is other. Nick posits the methanotroph, the acetyl-CoA pathway, as the most ancient one. We have put forward a different scenario which actually is very close to the acetyl-CoA pathway, but which uses an additional electron donor, which is methane. So the differences are, I would say, minor. In principle, we agree on most of the things, but one of the things I'm interested in this is that in this pathway there's a couple of redox loops, and these redox loops may be interesting to explore a little bit in more detail, whether they can work as dissipative engine if we just simulate them, if we can get the structure formation coming out of these things. Okay, so my point in here is that we might not necessarily have to look for all the complicated organic molecules, because if you come from the physicist's point of view and you look at life as a dissipative structure, then life does all the stuff itself. What you have to look for is, where is the energy coming from? The energy is redox energy for the case of life on this planet, and I would argue that it's the most appropriate one for the reasons that we've been discussing it. And then we have to find all the crucial dissipative engines from looking at extant life and give all these informations to people who try to do reactor experiment and recreate life from scratch, or the first stages of life from scratch. Okay, so to finish this up and to have plenty of scope for discussions afterwards, that was the thing I was just mentioning. Then there's the next thing I was already talking about, is the water. So I would hold that redox energy only is a good source of energy for life if you are in water. Because in an aprotic solvent, everything will go within milliseconds or sub-milliseconds, microseconds. If you have a minute, it's Marcus theory electron transfer. So if you have these things in atomic distances, then with sub-microseconds you have equilibration going on. That is one of the reasons that I wanted to make you think about all these. I mean, I hear a lot about that the Titan is great because it's full of organics. So if there is no redox, no interesting redox chemistry happening in liquid methane, because everything, as I said, everything goes to equilibrium. We need something which is out of equilibrium and which stays out of equilibrium. And now there's one point. Some of you in the community have understood that we need, or have taken the message that we might need the redox disequilibrium. And they put forward oxygen as a very, very good oxidant in extra terrestrial environments, like on Mars, because there is oxygen on Mars. Now, there's one problem, and we know that, biologists know that. Oxygen is an extremely good redox collapser. Oxygen gives you a lot of redox energy. I have to finish? Okay, so I'm finished actually. But it is a mediator, so it will do away with all disequilibria in a very, very rapid way. This is why you get cancer, this is why you age, and all these kinds of things. Okay, and we shouldn't forget about the metals, and so the metals should be taken into account, I would say, for knowing which kind of galactic regions are possibly locales for life coming up. So that's thanks to especially to Mike Russell and Albert Branscombe, who worked out most of the theoretical parts of these things. That's my group in Marseille. And we had many, many very stimulating discussions with Nick Lane and Bill Martin, even if we don't agree on everything, but we agree on most of the things, I would say. Thank you.